All right. Welcome, everyone. Thanks for joining in. This is Bayesian Lund webinar. It's a continuation of a series of webinars that we had over this fall. We started with discussing BRMS in September, if I'm not mistaken, and then, or maybe even August. And then we looked at Bayesian visualization last month with Gigi Dist, and Matthew K was presenting his packages and the development in that respect. And then today we're talking about Stantargets, and we're very pleased to have Will Landau with us. He is going to take us through the Bayesian model validation pipelines. As I said earlier, please put your questions into the chat. We will pause for questions in the middle and take questions as they appear. Also, towards the end, there will be a bigger chunk of time for questions, but if there is anything else that you want to ask or comment on, please put it into the chat. This webinar is also co-hosted by Oslo Use R and Skåne Use R, our user groups. And if you're dialing in from a different location, please put hello into the chat with your location. We're very welcoming, very happy to welcome you here as well. Talking about the upcoming events, next month we're going to have a webinar that is more focused on Bayesian workflow. Aki Veatari will present his on Bayesian workflow paper, which is super exciting, but maybe not less related to implementation in R. And that webinar is not yet public, but we'll make it public soon. So if you're Bayesian and you want to hear more, stay with us and we'll have more exciting events coming up. Now that out of the way, I'm very happy to introduce Will. Will has been very prolific developer in our community. He's transformed the way people do analysis. That's not just my words, but if you follow Twitter, you'll hear a lot of praise for targets and Stantargets. And Will is today, we're very privileged to have you here. Thank you so much, and the floor is yours.
Well, thanks so much for having me on. I'm excited to be here, and thank you for the generous introduction. Today, I'm going to be talking about the targets ecosystem as it applies to Bayesian statistics, specifically with Stan. You mentioned the Bayesian workflow talk, which is coming up next, and I think that's a really nice segue from this talk, because what I'm going to talk about today are some of the computational aspects of the implementation side of Bayesian statistics, whether it's analyzing a few data sets with a few different models or running a simulation study to examine the behavior of a model that you're developing. And I have an extended example on that to share. And there's so the R packages that I'm going to focus on are targets, and then an extension to the Stan ecosystem called Stantargets. And I'm also going to talk about how targets integrates with R Markdown. All of these are pretty new features in the targets ecosystem. And I'm going to show how this is a successful pattern for running calibration studies on Bayesian models. And the reason I went in this direction is because workflow systems have trade-offs. R Markdown is a very commonly used workflow system, but it struggles to handle the kinds of heavy computation that Bayesian statisticians often do. And targets works really well with the system, but it's a lot of user side code to write. It's a lot of careful planning and development up front, and it's pedantic. It's a bit different than the informal exploratory analysis that our users are, or users of any interpreted language in the data science and statistics areas are often used to doing. And what I'm trying to do with this extension to the ecosystem is to combine the best of all those worlds, the power of targets with the ability to tap into Stan really easily, and to abstract away a lot of what was keeping people back, and to have the readability of an R Markdown report at the end. And this is not just for, I mean, the target, I'm going to talk about targets first, just so we can get our bearings here and then build up from there. So targets is a workflow system for all kinds of long computation in R. And not only for Bayesian statistics, but also for machine learning and PKPD, for those of you who are also in the life sciences like I am, simulation of clinical trials, statistical genomics. And in fact, I was working in statistical genomics on a Bayesian problem in grad school, and that's what kind of motivated my work on these workflow systems to begin with. And a few different applications from database queries to ETL have come up as well. So it's really all across the board, long data analysis workflows in R, if we're talking about core targets. The underlying problem is the process of iterating on a large data analysis project. So there is a perception that when you have a data analysis, you just run the code and you have the results and you're done with it. But I mean, you start getting into problems because for much of the time, it's very common to encounter setbacks because the code usually runs slowly. So you might wait for several minutes to several hours to see a result. Preaching to the choir here with Bayesian statisticians, but it is important. And then, I mean, not only is the code slow to run, you're never really done running it because there are always bugs to fix and follow-up questions to answer based on things you discover. There are new data. There are new sort of extensions to the model that you might want to pursue. And so the first time running this project is not enough. It's we frequently go back to our workflows and run them again and again. And because of the long computation time on each iteration, it's easy to get stuck in a Sisyphean loop where you spend a lot of time waiting for jobs to finish and struggle to get a hold of a complete set of results that are current and up to date. You really feel this for delays of an hour or more, but even if you're waiting for just a couple minutes, the iterations compound on themselves, and it's hard for the results to catch up in this process. And we can start to break this down if we think of a data analysis workflow as a pipeline that begins at the data sets that you create or collect and runs through your models and post-processing and ends with some figures and tables and reports that you communicate either with yourself or put into a research paper or share with your colleagues. In this pipeline, the steps are interconnected. So if, for example, you change the code for a model, then everything that depends on it is no longer valid. So if you change the code for the model, you're going to need to rerun that model. And then all the other steps, the post-processing and visualizations and reports that depend on that need to be refreshed to reflect the most up-to-date current results from the model. Workflows are complicated enough that usually it's difficult for a human to do this. What steps need to rerun? What steps are still up to date? What code have you changed since the last time you looked at it, which could be several months in the past? I don't think that it's convenient or reliable or reproducible for humans to try to do this exercise of going back and seeing what components of the analysis they can skip in order to save time. There is a need for automated tools to do this for you so that you can have a reproducible, up-to-date end product while skipping as much runtime as possible when things don't need to rerun. And to make those objective decisions about what to run and what to skip, we turn to pipeline tools. This is exactly the job of a make-like pipeline tool. So this kind of pipeline tool does several things. It identifies the inputs and outputs of each step in the computation, where each step is called a target. So a target could be a model that you fit or a data set that you create or a figure or several figures that you create, just an irreducible task that you run, a skippable step of the computation. And each of these targets has clearly defined inputs and a single output, just like a pure function. And as the user, you code up these pieces, these targets one by one, and then it's the job of the pipeline tool to arrange the targets as a whole workflow and figure out how they fit together. And this is represented in the directed acyclic graph that you see, and it reflects a flow from left to right that the workflow proceeds on as it runs. So a pipeline tool can either do that by, the user explicitly identifies dependencies, or in the case of the targets package, there's a static code analysis engine that runs that detects, okay, all these models depend on this upstream tidy data because the symbol tidy data is mentioned in the commands for each of these end products. So it figures out how the workflow is arranged as a whole, and then it can run the entire workflow, or the parts of it that actually need to run from left to right in this graph. It'll skip the steps that need to be that don't need to run, the ones shown in green here, and it'll automatically run the correct targets, the ones in blue here that are not up to date, in the correct order. And that means running the models before the plots, before the report in this case. And another really nice piece is that conditionally independent targets, or conditional dependencies, can run in parallel. So a good pipeline tool will do this parallel orchestration and run targets in parallel or in distributed computing when it can, and then if one target depends on another, it'll automatically detect that and run those sequentially. Some pipeline toolkits have some of these features. So for example, Airflow-like tools may sort of always run all the targets. So, different variations on this theme. There are actually hundreds of pipeline tools for other languages. If you're curious, you can explore this link. And oddly enough, there's not a whole lot of, it's an extremely active, sophisticated space, but most of these tools cater to either Python or try to be language agnostic and act as command line tools or graphical interfaces. There historically hasn't been a whole lot for R, despite the immense need for this, for the kinds of things that we do and we've been doing for years and years. So that's where the targets package comes in. So targets is a make-like pipeline tool with all the features I described in the last slide, and it builds on its predecessors, Drake and Remake, which were to my knowledge, two of the few pipeline toolkits that existed for R previously. And like its predecessors, Targets is specifically designed to work within R, and it respects a lot of the domain-specific features of the R language, including integration with R Markdown, like I'll show later. It also encourages good programming practices. It gets us away from a common script-based mentality, and it embraces programming in terms of functions, which ends up being a lot cleaner in terms of the code that you write, and it also abstracts away files as R objects. So when you code up your workflow, you're not thinking about files, you're thinking about the objects that your functions will produce, which is very natural for how a user works with the language. And at this point, I'll answer one of the questions in the chat because I'm about to switch gears. Somebody asks, when and where will we use Bayesian, random forest, and deep neural net on the previous slide? What is their difference and similarity? Which one is preferred? So this is, for example, if you want to do a climate projection. So this is a sketch of a pipeline. I don't really have this coded up seriously, but in this example workflow, you might be sort of analyzing a data set and sort of making predictions based on the data for some task, either to find the best predictive model in this situation. If you're interested in accuracy and classification error, you might compare these machine learning algorithms to the posterior predictive distribution of a really good Bayesian model for this specific problem. And but it really depends on the research application. I'm talking in this slide, I'm talking in general terms. Every workflow is different. Every workflow is designed to answer a different question, which will depend on the domain knowledge. Another great question is targets somehow more geared towards the tidyverse users, or does it also work equally well for base R workflow? So targets does have some built-in tidyverse features. So some of its functions are powered by the tidy select package to make things a little bit more convenient. So if you know tidy select, keywords like starts with and contains, you'll be able to use some of the nice syntax of some functions of targets, but you as the user have a lot of control over sort of most of what goes on in the workflow through custom coded functions. And it's up to you whether to use tidyverse or base R, or for large data sets, data table, or things like that. And so core targets affords you with a lot of control over that. So, and you can opt out of the R Markdown or tidyverse features that are built directly into targets. There are ways to do that. Yeah, some great questions. So I'm about to switch gears. That is why targets exists and the advantages. But there are challenges, and the main challenge is that there's a lot of programming left to the user, and which is not unusual. I mean, if you're developing a Bayesian workflow for a research paper, you'll end up writing a lot of your own code to specify the model and run it and post-process it and produce the figures and tables for the paper. But targets enforces a very function-oriented style. So instead of writing imperative scripts that sort of produce files, you may have seen the numbered script paradigm in sort of workshops on what they forgot to teach about R, for example. Targets, on the other hand, encourages a style of programming that's more similar to package development, where you're writing pure functions that accept formal arguments and returning a nice R object that can be stored and then used as the input for, let's say, the next function. So that's how it's a really nice style once you get used to it, but it's not part of most people's training, and it introduces sort of a bit of a hurdle to getting started. And it makes it more difficult to, if you have sort of an imperative-based programming project, to refactor that into something that targets can accept could take a lot of work. So that's one challenge, and it's a lot to ask. It's a lot of software engineering. It's a lot of software engineering to ask of a statistician or data analyst. And targets also requires a lot of discipline. So in terms of how you inspect your workflow for potential problems. So for example, in a workflow like this, you want the graph to be connected, and the graph is sort of, it is automatically generated by how you write the code in your workflow, but some things can happen occasionally where this graph is disconnected incorrectly, and so it's up to the user sometimes to understand a little bit about how static code analysis and global variable detection work in R in order to get the kind of workflow that you expect to have. And that can put a barrier on sort of how easily you can get started with targets. And I'm going to address two different ways that I've tried to address this problem, both in terms of writing writing packages that give you ready-made pipelines already, especially for a Bayesian setting, and also the literate programming side, which could decrease the amount of software engineering that the user has to do. So I'm working on, very slowly but surely, and a couple other people have joined me, to extend targets to make constructing pipelines easier in specific situations. So this collection of packages I'm calling the targetopia, which is an ecosystem of packages that's built on top of targets. And like I said, the goals of these packages are to construct pipelines for domain-specific situations, like Bayesian data analysis with Stan and Bayesian data analysis with JAGs. And the mechanism behind packages like this is something I'm calling the target factory. And a target factory is just a mechanism that defines one or more targets at once, using very simple inputs from the user. So what you have is, for example, in a workflow like this, where you read a file and run a model on the underlying data, there are steps to track the file for changes and to read the data in and then run the model. Those require some thought from the user. If you were to custom code it, sort of, how do I make sure that the file, that changes to the file cause the model to rerun, and how do I code up targets individually for the data and the model. With a target factory like this, all you need to input is the name of the file, and you automatically get a section of the pipeline with 3 different targets. Ideally, a target factory is part of a package, and so when the user loads your example package with that target factory, they only need to call this target factory once on some data, but they get 3 different targets for free. And if you've tested and developed the package correctly, the user can be confident that these targets are connected in the graph appropriately. And that cuts down a lot of the cognitive load that users experience when they run, when they use targets. And one of the first places that I've tried to use this idea to tackle is with Stan. So my training was in Bayesian statistics. I still develop and refine and implement models in the life sciences industry. So I'm still active internally in Bayesian statistics, and the Stantargets and Jags-targets packages have been things I developed to help my colleagues and I, and as well as people in the open source community, develop Bayesian models with Stan and Jags and use them in workflows. Stantargets in particular is based on packages command stand R and posterior, and it makes Stan models easier to use within a targets workflow. A bit about Stan. I know I'm preaching to the choir. Many of you have heard that Stan is a probabilistic programming language that does Hamiltonian Monte Carlo and no U-turn sampling, which has a few advantages over Gibbs sampling that we're familiar with. But it also does variational inference and optimization as well. And what I've tried to do with Stantargets is closely mirror the functionality of command stan R, and have implement the first layer of bringing this into the targets ecosystem. And so what we have here are target factories for running 1 or more models on a data set with either MCMC or variational inference or optimization, in addition to some other target factories for example, generated quantities, for example, transformed parameter, for example, if you were to write some statement in your Stan code to simulate from the posterior predictive distribution, you might use this. And a couple other target factories. There are also a few different target factories for running extensive simulation studies to interrogate the behavior of a model using each of the algorithms that command stanr supports. This is a really common pattern in my group because we spend a lot of time validating the models that we develop for use in the analysis of clinical trials. And it's critically important that we make sure the implementations of these models are correct before we use them to analyze a trial. And so one of the things that we've been able to use is simulation studies to start to try to get at the calibration of a model, like I'll talk about in a few minutes. One of the things that some of these target factories do, like tarstan MCMC rep summary, this target factory is going to encode a workflow that does a simulation study that simulates a lot of data sets, analyzes a bunch of models, and it runs one or more models on all those data sets, and then compute posterior summaries on all the parameters. And there's a function reference on command stanr, and like I said, there's also and each of these functions kind of mirrors what command stanr does. And so in typical target factory fashion, so if you include, for example, tarstan MCMC in one of your pipelines, you're getting multiple targets, even though it feels like you're declaring only one. So you're getting targets that track the model file for changes and the example data, the data that you're using, example or real, where you'll run the model and you'll get actually multiple outputs from the model. Not only you'll get posterior summaries, you'll get the actual draws, and you'll get HMC diagnostics as well. All this only requires you to write one function to simulate from the prior predictive distribution of that model, or to get the data set in some other way, depending on what you're doing. And this is often the most straightforward step in a workflow, and there's no custom code required for any of the other pieces. You just get a workflow for free. Likewise with tarstan MCMC rep summary, and I've used this to run models on thousands of simulated data sets at a time. So it looks like we're only getting a few targets, but each of these dynamic branching patterns here actually have thousands of dynamic targets. And I can talk about dynamic branching in a bit for those of you who are curious, if we have time. But it's a way of defining new targets while the pipeline is running. And it turns out to be good for a large number of tasks that are very similar to each other. So going into an example where this is applied. So this is a model that it's a Bayesian longitudinal model for the analysis of clinical trials. It's very similar, for those of you who are in the life sciences, it's very similar to an MMRM, a mixed model of repeated measures, except that it has this one has no random effects. Very often we see this model used with full conditional conjugacy, where the covariance matrix has a structure like unstructured or AR1 or what have you, and maybe for the unstructured case you use an inverse Wishart distribution as the prior. Now, inverse Wishart, even though we commonly see it that way, it used in this kind of model, it induces problematic prior associations among the correlations and covariances. And there's a great archive manuscript by Alvarez and others that describes this. And so I've convinced my group that we should be trying to get away from that and to use something that has fewer biases for these components in a covariance matrix. And one thing that we like, and it was recommended out of this paper, is as a separation strategy where we model the covariances and correlations separately, and we use something like an LKJ prior on the correlations and a sort of a diffuse prior on each of independent diffuse priors on the correlation on the standard deviation parameters or variance parameters. And so this is helping to remove some of the edge cases and inherent biases in those priors. And Stan has some really nice functions in the Stan code to actually invoke this LKJ prior either through the correlation matrix itself or through a Kolesky factor, like this lambda t by t, which you see here. So this is very relevant to what I've been spending a lot of time with in my day job, even though this looks very general. This is kind of a great point in terms of how we're transitioning. So we can code up this model in Stan. It's pretty straightforward, but we need to ensure that the model is implemented correctly. We need to validate this model, and it involves checking for a lot of different issues in a lot of different ways. And one of the things we're looking at is sort of is the Stan code in this model, does the Stan code in this model match the model specification that you're seeing on this slide here? Do the code in do the model spec and the Stan code agree? And the way we do that a lot is with the idea of calibration. So what I'm going to present as this Stantargets workflow is we're going to simulate data from the prior predictive distribution. We're going to do that thousands of times, and we're going to fit the model to each data set using HMC. And for each model that we fit, we're going to calculate posterior intervals on each scalar parameter. So each correlation component, fixed effects, each variance component. And for each of those parameters, we're going to look at how many of those posterior intervals cover the true parameter draw from the prior predictive distribution that we originally obtained when we were simulating the data. And if, for example, if we're calculating 50% posterior intervals, if the posterior is correctly calibrated, then we should see around half of the intervals that we've computed covering the respective true parameter draws. And likewise for 90%, 95% posterior intervals, or however many you choose, X% of them should cover that parameter if the credible level is X%. And this is based on the concept of calibration. And there are some papers on this, and there are papers that extended this to full-on formal simulation-based calibration, which extends this idea. I really like the blog post by Bob Carpenter that I've linked here. He really clearly explains why this technique of calibration works when you're checking a model. It's unless you have really improper priors or extreme priors, then the posterior is calibrated by definition. If you're simulating from the prior predictive distribution and then analyze that model, sort of analyze that data with the same model, then the prior and posterior should agree. And that's why this works. And what I'm sharing right here is a very simple version of testing calibration that's sort of informally used a lot. There is the technique of simulation-based calibration, as it's coined, takes the idea further and has a bit more of a sophisticated way of getting at this through rank statistics. I'm showing a much simpler version of it. And that's sort of one piece of the workflow, and I will get to that very soon. The other, when I'm building this workflow, just so everyone understands, I'm going to switch gears here again and talk about target markdown, because we're going to implement this validation study in an all-in-one R markdown report when we start coding this up, and this is going to make the end product a lot easier to develop in some cases and a lot easier to read at the end. So targets in its typical, we're using targets in its original form. The workflow engine targets doesn't really have an opinion about where you put your custom functions. It only requires that you define a file called _targets.r, and that you source any functions that you need into the session, and then end that script with a pipeline definition, which is just a list of target objects. It doesn't really have an opinion about how you get there. And a lot of software engineering questions are left to the user in terms of, okay, how do I write my functions? Where do I put them? Where do I put my code? What files do I name them? How do I set this up? Those are questions that targets doesn't answer, and that our Markdown does, because in our Markdown, you can just put everything in a report with sensibly organized code chunks. And it's really easy for an analyst or a data scientist or a statistician to do that. And target Markdown is an extension of targets to our Markdown to allow this way of interacting with pipelines. So and it supports an interactive mode for prototyping and emulating what happens and emulating the process of running the workflow. And then there's a non-interactive mode for full-on pipeline construction. And both of those features together have uses in the different phases that you'll go through when writing a project with targets. There's even a template to get started. You can use the use targets function, or you can open a fully fleshed out minimal example project using the RStudio R Markdown template system. So here's part of the example report for that calibration study that I described before. So we use our Markdown to tell the story of the data analysis workflow, and use prose like the paragraph in line 121 to sort of tell the user what's going on here, what we're trying to do at this point in the workflow. And what I'm explaining here is we're beginning by simulating by writing a function to simulate data from the prior predictive distribution for this calibration study. Fortunately, this is by far the hardest piece of custom user-side code that's required in this workflow. And it's not even the hardest thing that you'll do. So simulating from the prior predictive distribution of most models is more straightforward than writing the rest of the workflow to analyze that model or implementing that model to begin with. And we're going to need this for our calibration study. And so what we're doing here is we have this function inside a code chunk. We're using the targets engine. So targets has a special knitter language engine to support target Markdown. And so instead of R right here at the beginning of the code chunk front matter, we'll write targets. We'll give the chunk a name, in this case data, and then we're going to tell it that we're not actually defining a target here. We're defining some global objects that support a target. And so we're going to give the tar globals code chunk option the value of true. And then when you run this by clicking the play button here on the right, what will happen is it will emulate this part of the pipeline. It will run the code inside the chunk and assign the objects to the environment. And it'll tell you that's what it's doing. If we go to define a target, then what will happen is yes, you do also get interactive mode and non-interactive mode. And here we're defining, we're invoking the target factory that declares and runs this entire simulation study to make use of the simulate data function that we defined on the earlier slide, and turn that into a workflow where we're applying this model to each of thousands of, or in this case, 1,000 data sets to analyze this model, to analyze each data set with this stand model that we have, and post-process each of those runs and assess the calibration. So, actually, the calibration is a couple of downstream targets, but I'll get to that. But anyway, so if we don't have the tar globals option equal to true, then this will define a target. If we run this in interactive mode, then clicking the play button will actually run this target and assign the objects to the environment. That's great for prototyping. But if we just want to construct the pipeline to execute later, what we'll do is we'll say tar interactive equal to false. And what that's going to do is it's not going to actually run the code in this chunk. And in fact, sometimes that's unwise for something this large, because it can take several hours to actually run this in your session. And so what this actually does in non-interactive mode, which you can control, is it will write scripts for you to set up the pipeline. So it'll establish a targets file, which is sort of the centerpiece of your pipeline, and it will write a supporting script that contains this target definition. And this runs really fast. And what you're doing at this point is you're building up the pipeline gradually before you actually run it. And there are a couple more targets that you may need to define. For example, a target that assesses convergence diagnostics, and a target that evaluates coverage. And thanks to the way the summaries are organized, this coverage calculation is actually quite simple using some of the tidyverse. And this looks like ordinary code and not necessarily a target definition. But if you have this, if you activate this chunk option, tar simple equal to true, what will happen is targets will automatically turn this code into a target definition, and it will run it. It won't run it right away. It will store that in a script that becomes part of the pipeline. So this target markdown engine is equivalent to sort of breaking up a project-oriented workflow into script files, except that the process of breaking it up into script files is automated for you. So you don't have to worry about where to store things, and through a lot of the software engineering components of sort of how you organize your code. And it's your choice whether to run the pipeline outside this report. So you could just run this report to define the pipeline if you wanted, or you could run it outside of the, or you could run the pipeline inside the report itself. It's often convenient to run it inside the report. So that's what I've chosen to do here. The function tar make cluster MQ actually, if you configure the cluster MQ package to work with sort of an SGE or a Slurm cluster at your institution, it can do distributed computing. It can send multiple targets to sort of different nodes on the cluster, and it'll run all batches of computation on different nodes, which is it's vital to some of this work, especially for a model like this. So I've chosen to run on about 100 workers. That turns out to be pretty good for a pretty good load for the system that I have access to. Other system administrators and other institutions might want you to use fewer workers at a time. So that's a conversation that you might want to have with whoever maintains the computing architecture where you work. And finally, after the pipeline is run, we can read and report the results for convergence and coverage.
Can I?
Want to come? Yes.
Could we pause for a second? I mean, it's a lot of material to take in, but just to clarify on targets markdown, and I think I want to encourage again people to type their questions in the chat. But while the questions are coming in, may I ask a question about the targets markdown? So as far as I understand, targets markdown is documenting the process of creating the pipeline, and then optional, as you showed a couple of slides ago, you can also include the tar make cluster MQ command into the same markdown in order to kick off that pipeline. So the first run of your Markdown file will take 10 minutes or 10 hours, whatever that, I mean, depending on the complexity of the pipeline. But the subsequent runs will take nothing if there are no targets to rerun. Is that the idea? Is that what you're thinking in the target Markdown, the way you present it right now?
Yeah, that's exactly it. That's a really good way to describe it. So
right. So if I also want, sorry, if I just continuing my question. So if I also want to, make a report that basically presents the results, I can either continue to make it in the same file, or maybe this Markdown could create another Markdown that will present summaries, like plots from it, and I don't know, some sort of diagnostics and stuff like that. How do you envisage combining these two tasks? So one is create a pipeline, run it. Another one is report from it and present. Do you envisage them to be in the same file, or do you envisage those to be two separate tasks? Because both are important.
So I envision something like Target Markdown to be more primarily focused on the developers and very technical collaborators, people who are in the process of implementing this, and to be able to describe how you're implementing it, if somebody else wants to, and describe what somebody else might need to know if they're actually constructing a workflow themselves, enhancing reproducibility and all of the minute details of what goes on there. But the alternative, like you suggested, is to have a report, a literate programming report, as part of a pipeline. So you could have a target that runs a report based on the values of upstream targets, and simply shows those target values and explains what they mean. And this has actually been possible for a longer period of time. There's an older feature in the targetopia package called tar render. You're putting the function name in the chat. So what that function will do is it will take a report that loads targets from elsewhere upstream in the pipeline, and it will what it will do is it will detect that this report sort of depends on certain upstream targets, place it in the dependency graph in the correct place, and then when it comes time to run it, it will run and it will read those targets from the data store. And what's nice about that is not all the details of pipeline construction need to be there, and you can run it based on how it's constructed. You can either run it outside the pipeline using the knit button in RStudio, or you can run as part of the pipeline reproducibly. And so you have different options about interacting with it. And if you use tar render, that's more like a polished end product with not all of the gory detail, but just enough for a casual viewer or a higher level viewer to understand.
Great, thank you for this. Another question that I had also regarding Markdown, and that is, does it have to be Markdown, or can it be a notebook? And the reason I'm saying is that it doesn't, I mean, what's the place of reproducibility here? Do you need it to be run? Do you envisage that the fact that it's rendered from A to Z means that everything has been rerun, and you would put it under version control, and that way you would ensure that the targets have been not modified? I mean, where does the version control come in? I guess that's my question. Because if you place it if you do it in the notebook, then there's no necessarily requirement that all targets have been run sequentially and things like that. But the rendered report allows you to kind of ensure the validity of the latest run. Can you talk a little bit about how the version control comes into the Markdown as a pipelining tool?
Sure. There's a bit to unpack here, and I'll see if I can answer some of this.
Maybe towards the end. So if this derails the conversation, no, this is defer it to the end.
No, this is all good. I just want to make sure that I address this. So in terms of it having to be our Markdown, I advertise it as such because it's the more popular way of interacting with it. But I mean, Target Markdown what I'm showing in the slides can be used with RNW files in addition to RMD. And so as long as you can use knitr, you can use target markdown for, let's say, non-markdown documents. Tar render does invoke R markdown render, and it would require that actually be in R markdown. In terms of notebooks, so the interactive prototyping works in the notebooks. So target markdown in interactive mode might allow you to say, so what is this? For targets that run quickly, it'll allow you to sort of iterate on your code while modifying the actual pipeline as little as possible. And so you might, let's see, go back to one of the targets that describes how you are calculating coverage. So if you have a bug in your summarize statement, but all of your other targets are, you have some test data in memory, you've loaded the upstream targets into memory to iterate on that. You'll be able to use this like a notebook. You'll be able to click the green play button and just run this target or a collection of targets. If you wrote a whole collection of targets in this code chunk, and it'll put that object in memory. And so without disturbing any of the objects in the data store that you've already run in your pipeline. So that is sort of how you use it like a notebook. There is this interactive mode that lets you test and prototype. When it comes to actually running the pipeline end to end, though, that's why there is a non-interactive mode for pipeline construction, because that really should be run end to end. And if you're running the pipeline sort of in a serious way, if you're confident in this state of your code, you're ready to commit to several hours of running something. You can even sort of knit, even if you have an R notebook, you can still knit it end to end. The IDE, the RStudio IDE still allows that, and the render function in R Markdown still allows that. So it's just kind of it depends on your goals for sort of what you're doing at the moment, whether you're setting up a pipeline or running it for real. And I guess the last part of your question was version control. How does this relate? So, the most recent predecessor of targets is a package called Drake, and it suffered from some problems that I couldn't easily solve. And one of those was the architecture of the data store. That I was relying on an external package for this, and it created a lot of files that were cryptically named, and it was difficult to put under a version control system like get LFS, because there was just so much data. With targets, one of the things I've tried to do, and one of the motivators for creating this package to begin with, was to create a data store that created as few files as possible and stored them as efficiently as possible, to be friendly to version control systems that were sort of third party, like get LFS, like DVC, like others that really focus on data versioning and doing that right. Version control for targets projects, otherwise it's a difficult problem because of the size of the data. You can put your code under version control, commit it to GitHub or GitLab or Bitbucket, and interact with those tools like a software developer would, and like a lot of the sort of statistics and data science and R enthusiasts are doing these days. But yeah, putting all that data under version control is a big problem. And what I've tried to do with targets is just to get out of the way of, and to not cause problems for other tools, and to let other tools that are sort of third-party tools that really focus on this to tackle this problem. And it's an unsolved problem. I mean, it's data storage is expensive. It's unfortunately, targets isn't doing anything to directly sort of contribute to a solution. But I think it's an important enough problem sort of outside targets that people will keep working on it, and we'll get better and better options.
Thanks. There's a question in the chat, but could you kind of give a simple problem statements for business related problem which Target can help to solve better? And I think if I can just partially answer it, and Will, please correct me. Towards the beginning of the presentation, Will had a slide where you showed several targets that were running expensive tasks in parallel. One of those was random forest, another was deep learning and whatnot. There was a Bayesian task as well there. So if you are running expensive tasks that take a lot of time to run, targets can help you automate the process of pipelining and sequencing the task and ensuring dependencies are run in the proper order so that your results are always up to date and relying on the latest and greatest reruns. I think that's the simplest way of putting it. If that's Will, correct me if I'm wrong.
Yeah, I think it's a great way to explain it. If I were to put it into my own words, I would say that if it's sort of a business related problem, then Targets helps deliver faster, quicker, more reliable, more efficient and accurate results for data science and statistics workflows that are under development and are being run and iterated on a lot. And on my company, we do clinical trial simulation a lot, and we have basically this, but for simulation, and we have pipelines that simulate sort of thousands of trials and to understand the various implications of different study designs, to compare different study designs for a trial. And we present results to the team. They propose different questions and different scenarios, and now we have to go back to our original pipeline and deliver the results often the same day. So and we want to make sure our results are accurate and up to date, but we don't want to have to sort of rerun the whole pipeline when we're sort of adding new scenarios or we're changing some of the functions. We can just run that stuff on the cluster, get done as quickly as possible, and then be confident in what we're sharing.
I guess that what I want to add is that most of the time, it's the working code that is running. Like you're modifying something very small, and then you waste 99% of the time waiting for the code that you already know works to run. And then your little modification is run towards the end. And that's very frustrating to watch. So if you can break down your task and let's skip parts that do not need to be rerun, then you're saving yourself a major consumption of time.
Exactly. And a really common way this plays out is if we imagine that all the model nodes in this graph here are green and up to date. These are the most time-consuming steps usually. Some of the plots sometimes take time, but it's usually the modeling steps that are in a workflow that I sketched out here that look like this, that take the majority of the time, but not the majority of the work and the iteration. A lot of the times that the models are well established, you're building on sort of several years of history of this kind of task, and you're communicating to a new team, a new set of people, and a lot of the runs that you'll do are just updating a plot or updating the R Markdown report, and just to be able to run the pipeline and just have the report rerun and be confident in the upstream results really saves time. And I've been in this situation a lot for workflows that I haven't worked on in 6 months. And every time that happens, I question whether I have to rerun everything in order for the to get to something that I can share. But I go back to the project, and I use functions and targets to inspect what's being done. And a lot of the time I find out that almost all the targets, or at least all the really time-consuming ones, are already up to date, which saves me an entire day whenever that happens, because I don't have to refresh the results. I can immediately go to iterating on the plots and reports, which are the least time-consuming in terms of running stuff. And it's really increased productivity and peace of mind.
Great, thank you. Sorry for derailing the conversation. We can come back to Targets Markdown and pick up where we left off. But this was useful in clarifying. People in the chat as well are commenting that this is clear now. Thank you.
Thanks. Yeah, and it's powered by, as Russell is said in the chat, so these intermediate results, and each of these intermediate results is actually stored as a file in the data store and recorded and hashed, and those hashes are stored in the metadata, and that's sort of how part of how targets knows what to run and what to skip. And having these intermediate results, it lets you load them and inspect them independently. And it ensures that even if you close down R, you'll still have the intermediate results, and you can build on a pipeline that way. And actually, what to sort of pick as your intermediate results is oftentimes a little bit tricky, and that's sort of the job of Stantargets and target factories, is to figure out what kinds of objects it makes sense to have as intermediate results. Because if you had sort of everything as a single target, that would sort of not be useful. We'd be back to square one. But if you chop up the workflow into as many targets as possible, that's going to store a lot of different files, and at some point the performance of targets is going to slow down at around several thousand targets. And that's sort of why some of these target factories, when they use dynamic branching, we do this in batches. So if we go to this target statement here, so we're simulating data sets and running the model on each one. We've divided this actually into 100 batches of 10 reps each. And so this is really when the main part of the workflow here has actually 100 targets, and each target is running 10 simulations from the prior predictive distribution, each analyzed with MCMC. And how you batch things sort of depends on how fast the targets package is going to run, and sort of how and the level of parallel computing that you want. And there are some decisions to make there, but it's a lot easier to do this with a package like Stantargets that abstracts away all the details of dynamic branching that the user would otherwise ordinarily have to contend with. Okay, so where we were is actually running the pipeline, and I've chosen to do this inside the target markdown document. The first time we run this, it took about 7 hours to run, and this is because, well, this is the first time I was running this. None of the targets were up to date. Everything needed to run. 7 hours, despite using 100 nodes on the cluster to farm this out. So some of these models can take quite a long time to do some of the tasks you need to do as a Bayesian statistician. During this process, I monitored the progress of the pipeline, not only through the tools on the cluster. We used an SGE cluster I could call QStat to see what nodes were running, but I also used functions like tar poll and tar progress to see which targets were at various stages of the pipeline. We're at various stages. Are they running right now? Or are they skipped? And tar watch is actually a Shiny app that does this. It'll show you the graph if you want it. It'll show you various summaries of progress in terms of which targets are running and which are skipped and which have already been built. The second time I ran this, I just ran it right after the first time. I hadn't changed any code or data. I believe I only made a change to the actual target markdown report text, the actual prose inside it, and it skipped all the targets, and it did that in half a second or so, or a second. So this is affirmation of reproducibility in a very short amount of time. It's telling you that it doesn't need to rerun all of your targets to get an up-to-date, usable current set of results. And the fact that your results match the underlying code and data that you have, that gets at a really important definition of reproducibility that's over and above the sort of literate programming kind of reproducibility. And with target markdown, both kinds of reproducibility are compatible. And to inspect the results, we had sort of one potential scale reduction factor in this workflow above 1.01, just kind of the not really a hard and fast threshold, but one to keep an eye on. And over these 1,000 runs and hundreds of parameters in this model, to have only one simulation with any R hat value above 1.01 is pretty good. I could have checked effective sample size as well for some of these runs. For the sake of simplicity for this workflow, I chose not to, but other convergence diagnostics are clearly available to us, and we know a bunch of those. And in terms of coverage of the parameters, you can see that about half of the 50% posterior intervals cover the truth, and likewise 95% of the 95% posterior intervals do as well. Some of these figures dip a little bit below, but this is really about long run averages rather than sort of being above a certain value. In fact, coverage too high is also a problem rather than coverage too low. I've caught bugs in working on workflows like this where I've seen coverage, both too high or too low, and have had to go back and rework some of these models. This kind of calibration study doesn't catch every kind of error, but it catches a lot of different kinds of model specification or post-processing issues that you might have.
And the repetition ID, there was a repetition ID on the previous slide, allows you to go back and inspect a particular run that reported a max R hat above the threshold. Is that what you're saying?
Yeah. So Stantargets assigns it assigns IDs to replications. Sometimes in regular targets workflows, you'll have to encode that yourself in the return value to generate a rep ID and then hunt back. In dynamic branching scenarios, it can be kind of difficult to sort of go back and recover that. But you'll have the rep ID. You'll have if you can locate the target that corresponded to that, you can get the random number generator seed of that target. You can reconstruct the data and then find out what's going on. So sometimes you might simulate from a prior predictive distribution that's numerically unstable if you have diffuse priors, and the data that you actually get out of that might not make sense. And so for the purposes of this calibration study, you might choose hyperparameters that for prior distributions that aren't as diffuse as your analysis priors, but as long as those priors agree between simulation and analysis, then you can still test the correctness of the implementation in terms of this calibration study. And that for more complicated models, that might take some experimentation to find a reasonable set of priors to simulate from that's numerically stable.
Thank you.
So there are a whole lot of different resources. These slides are public. The source of these slides are public. There's also the full target markdown document for this pipeline is also available in addition to its source. And of course, there are documentations on each of the components that I talked about today, sort of targets itself, target markdown, Stantargets, and the various Stan ecosystem tools that I covered. If you're new to targets, then I highly recommend going through this how to get started section. So part of this New York statistical programming meetup describes sort of basic targets in a little bit more detail. That might be good to start with. There's a walkthrough chapter in the manual, and I've made RStudio Cloud workspaces open to the public. There are a bunch of examples. There's a workshop, and there's a cloud workspace for that workshop, so you don't have to download or install anything. You can just go to the link, and you'll be in RStudio in your web browser. And to get started and to be able to run sort of a basic targets workflow, maybe just go through the first 3-ish items in this list, and it'll take about an hour or two, but probably not much more than that. And in terms of the actual report, so what this looks like is is a full-on verbose description of what this of what we're doing here. So we spent a lot of time sort of introducing and citing the various the techniques that we're going to use, and this is a good time to sort of introduce why you're doing what you're doing. There's the full specification of the model. We have the stand code to run this model. And the model specification statement, it actually, so is here, and we assign our prior distributions, and then in the likelihood we do some work to handle missing values. We in typical Bayesian fashion, we impute these as we're fitting the model, just like model parameters. Explains the calibration technique, why we're doing that, and then it starts to get into the code. And this, if we saw the source of this code chunk, we're actually using the targets engine here, which is why we're saying we're establishing these global objects in these scripts, in these different scripts, these global objects and settings. And then likewise for the data generation function, this is the full function that simulates data from the prior predictive distribution, and we're sort of simulating model parameters using hyperparameter values, and then we're going on to simulating data, and we're saving the data and the parameters in a Stan data list. So this is very friendly to Stan. The .join data list is something specific to Stantargets, specific for these calibration studies. So you can save the model parameters in this list that went into the prior predictive distribution. And then what Stantargets will do is that it will append these prior predictive draws to the summaries data frame, so you can more easily compare them to the posterior intervals that you get in that summaries data frame and calculate coverage. And so those are all the globals. Then we get onto the target definitions, and there's not as much to do here as there would be if we just use targets by itself. So there's, we call this target factory the tarstan MCMC rep summary. And this has, so you give it the function to simulate a data set, you give it the Stan file, and you give it a name. And the other arguments are mostly things that command stan R understands, like the iterations of warm up and sampling, for example. And then the summaries is something that is passed to the posterior package. For example, quantile 2 to get these quantiles for posterior intervals, and you can give it convergence diagnostics as well. And then we have some other targets to post-process and to get coverage and convergence diagnostics.
Well, before you scroll too far, can I
Yes.
ask one question that will be useful for recording? I know that I will come back to it. But one thing that you made a decision here, and that important, maybe not visible in the code, but when you generated the data, you created a function that is called data something. Can you scroll up there?
Yes.
There.
Simulate data.
Simulate data. So you formatted it as a function. You did not make it into the target. But for example, a convergence is a target, which means that, well, what's the difference? So there's a decision right here. You could have made this to be a target as well, right? And instead you decided to be a function, and you used it in the one of the target factories. While convergence is a target, it's not formatted as a function. Can you talk a little bit about that distinction? That's a target question. It's not Stantargets question, but generally that decision between leaving it as a function versus making it into a target.
Yeah, and so do you put the content of the code in a function that's called from a target, or do you put that directly into the target's command? And that's for most situations, I recommend creating functions outside of a target and then calling those within each target. And there's Miles McBain has a nice package called fnmate to more easily work with functions for pipelines in this purpose. This simulate data function is quite large and complicated. I kind of wanted to work with it, interact with it, and test it through outside a pipeline. It's much easier to do it that way. And so this made sense to have as a function. And another couple of considerations are this is the most upstream part of the computation. And also the target factory expects an expression here with a whole bunch of other options. If I were to insert this code inline, it would be a bit cumbersome and difficult to read. Down here, I have this code inline instead of putting this in a function. In most cases, I actually do take this code and put it in a function, but I wanted to make the point here that that you don't actually strictly need to have your code in functions. You can put a regular R expression inside a target's command, and then that command is run just like it would if you had introduced a function call here. So I'm just demonstrating here a little more flexibility. And sometimes if you have a large number of these post-processing targets, it may be inconvenient to go too far into modularity and break things up. It might sometimes for little targets like this that are really simple, sometimes it's up to your personal style. It can be more convenient to have this in a target. Another consideration is if we go to the source of this report, then you might see why it ended up like this. So a target like convergence, for example, has this call to the target function. I give it a name, an expression, but that's not actually how I wrote it in the code chunk. How I wrote it in the code chunk looks a little bit more like this. So I didn't actually need to declare this as a formal target if I had the tar simple equal to true option. This sort of creates a target out of this imperative code that I've written here. And that's sort of automatically what happens in a target markdown report. And so I don't even really need to think about, okay, do I write a function for this? It's just code that gets converted into a target automatically.
Oh, that's brilliant. This is so
Thank
nice.
you. And so
the graph is interactive, right? So I was impressed that you zoom in, and that's very beautiful.
Thank you. This is powered by the Viz Network package in R, which is powered by the Viz Network JavaScript package. And I love it because you can, with some work, you can define hierarchical layouts like this that run left to right. It takes a bit of work, but it is possible. This is one of the few graphing packages in R that prioritizes this kind of layout for a flow diagram. You can zoom in and out. You can click and drag these to a layout that you may like a little bit more. And if you click on a node, then it will just show the neighborhood around that node. So, which is useful for really large graphs. If you have hundreds of targets and you only want to know the dependencies of stuff immediately upstream or immediately downstream, and there are arguments in this in tar Viz network that let you control how many sort of what degree of separation you want. So maybe you want every maybe the radius of your neighborhood might be 2 sort of upstream and 1 downstream. You can control that. And then down here, optional section to run the pipeline, which takes the majority of the time. And the summarization steps are down here, which pretty much involve reading the targets from the data store here and plotting them here. And the GT package helps these tables look nice. This part of the report, this section 4, looks very much like what would go into the kind of report that you talked about before, where it's a target that's that runs a report that just shows summaries and what they mean without getting into all the messy details of defining the pipeline prior to that. So if we imagine that this is just the report, you would write it exactly like this, where you have tar read and tar load statements here. And that would actually allow you to run this report on its own outside the report. But if you use targettypes tar render and put it in a pipeline, what will happen is that tar render will actually look for calls to tar read and tar load. It will recognize the symbols inside, which are convergence and coverage in this case, recognize those as dependencies, and then put this whole report at the end of the graph. So immediately downstream of convergence and coverage with edges connecting them. And it will know to run this report only after those upstream targets are available.
Makes sense. Thank you. Just kind of personal note, this has already transformed the way I view writing articles, because lots of time is spent on rerunning useless code, more or less. And yeah, thank you for presenting targets Markdown, because this will make everything so much clearer, and I can actually document my pipeline, which is super important.
Really glad to hear that. Thank you.
All right, I guess we're sort of nearing the wrap up here. If there are any more questions, please put them into the chat. Otherwise, yeah, if there is anything else, Will, that you wanted to mention, we could take that now.
So I guess I will mention that, like I said, the Stantargets is part of a collection of packages that I'm calling the targetopia, to extend targets to situations that to specific domains, to make it easier to write pipelines. And I've started with Stan and Jags because I'm more familiar with those tools, and I am Bayesian statistics is my statistical field. It's it's how I was trained, and related to a lot of the work that I do. And I'm a bit slower to branch out to other technologies and other fields, just because of what's relevant to my current work more than others. And if you have a kind of workflow that you like and you would like to sort of to make this easier to do in targets with some target factories in a package, then by all means, let's talk and let's see what we can do. I mean, for the Bayesian group, I thought about doing packages similar like this to maybe other probabilistic programming languages and black box samplers like Greta, for example, or packages like BRMS. Those are some ideas, but I haven't gotten around to implementing those just yet. And then there are other packages that are not generally Bayesian, like NL mixer targets, which Bill Denny has started to develop for PKPD. If you have stuff like this that you'd like to work on, or other ideas, and it'd be great to grow this ecosystem, then please don't hesitate to reach out. And likewise, if you think that there is an aspect of targets that could be improved, or just want to leave feedback, it'd be great to chat on the GitHub page. In terms of questions about targets, I'm most active here. I'd highly recommend, if you're interested, to post to the discussions page. We talk about issues and use cases all the time here. Happy to help.